So we've jumped ahead here to chapter 13. We think it makes more sense to cover the material in this order rather than the way the textbook does it. The reason why is because we were doing one sample testing in chapter 9, and then chapter 10 was two sample testing. And next we're going to talk about what happens if we have more than two samples. Now that splits, and the way that we handle a multi-sample proportion test is very different from a multi-sample means test. This chapter covers means. Chapter 11 will cover a multi-sample proportion test. But that gets into a different type of data and some other things that we'd have to introduce. And so it just seems more fluid to talk about basically what we call here a 3 or more sample mean test. So again, chapter 9, we did one sample means of proportions. Chapter 10, we did two sample means of proportion. And then now we're going to jump to chapter 13, which is 3 or more sample mean testing. And that's what a one-way ANOVA is. A one-way ANOVA is the procedure for testing 3 or more population means. In doing an ANOVA test, we will have to introduce a new distribution. This distribution is going to look a little bit different from some of the ones we've covered before. The two tables that we've covered before are the Z and the T table. Both of those are bell-shaped normal curves that are centered at 0. It's just how thick are the tails, right? But they're very similar distributions. The F distribution is very, very different. And so let's talk about the F distribution. Here you've got a picture on the bottom of your notes already there for you. And we're going to highlight some of these things. First one is there are an infinite number of F curves. So that's similar to the T. But notice what we say here. It's not an infinite number of F curves, one for each degree of freedom. It's each possible pairs of degrees of freedom. And you notice that if you look at the picture, it says R1 equals something and R2 equals something. Now, what you call the degrees of freedom, every textbook calls something different. This picture that I pulled called the degrees of freedom R1 and R2. They're probably more commonly referred to as numerator degrees of freedom and denominator degrees of freedom. But I've seen them called a lot of different things. The key is that there are 2 degrees of freedom for the F distribution. So this idea is that when we talked about the T, there was only one thing we were concerned about to know which T to use. For the F, there are 2 things we're concerned about to know which F to use. An F statistic is the ratio of the variation between groups to the variation within groups. You'll hear me say that a lot when we talk about F statistic. It's the ratio of variation between groups to within groups. The between group variation is in the numerator. The within group variation is the denominator. So that kind of helps explain a little bit why we have 2 degrees of freedom for every F. We have the numerator one and the denominator one because we have the one that references what's happening between the groups and one that references what's happening within the groups. The F distribution is right skewed, and all of the values are at least 0. Again, you can kind of see that visually there. I'm just having you write that down in words just to align with your picture. And of course, because the F distribution has all of its values greater than 0, the test statistic will also always be at least 0. And so some notation. K is going to represent the total number of groups. As we discussed earlier, the whole idea of an ANOVA is testing 3 or more means. So K cannot be 1 or 2. If K were to be 1, that's a 1 sample mean test. We learned how to do that in chapter 9. It has its own test. If K were to be 2, then that's a 2 sample mean test. We learned how to do that in chapter 10. So those are different things. So K has to be at least 3. Typically K will be 3, 4, maybe 5 or 6. There's nothing that precludes K from being 10 or 15 or 20. It's just not very common. Typically, if K were to be that high, there's probably a better test to use. And we're kind of in a slightly different scenario. So again, nothing that says it's impossible. It could be done. It's just those are rare cases. For the most part, K is going to sit in the 3, 4 range, maybe 5, possibly 6. I represents the ith group. We usually put that as a subscript. And so we'll say, when we talk about sample size, right, lowercase n, we'll say n sub I is the sample size, because it's n, of the ith group. And so anytime you see an I, we're typically saying, well, which group do we mean? And then we have capital N, which represents the total sample size, and that's n sub 1 plus n sub 2 plus all the way until n sub k. And again, k could be 3, so that could just simplify to n1 plus n2 plus n3. Could be n1 plus n2 plus n3 plus n4. We got to add up all the sample sizes, how many of them there are. Again, there have to be at least 3, or else we wouldn't be doing an ANOVA. We'd be doing a different test, one that we've already covered. And so next you see in your notes 3 paragraphs, all typed out for you. What I want to remind you of is when it's typed out for you like this, that does not mean that's not important material. What it means is you don't have to memorize it. Everything that you're writing down are things that you need to know because you potentially could be tested directly on that knowledge. What we have typed out here, I need you to understand the ideas behind these 3 paragraphs, but you do not need to memorize them. But they get to the core of what we're doing with ANOVA. ANOVA is kind of weird. We're actually not going to be testing the means, even though we are testing the means, right? And that sounds super weird. It is. But in ANOVA, you actually are testing variances, and that's going to allow us to make an inference about the means. And you say, how in the world is that possible? And that's what we're going to talk about in these next 3 paragraphs, and that's what I want you to understand. I need you to get this base concept of what we're doing and just in general how it works, the kind of 50,000-foot view. You do not have to get down to the weeds and be able to mathematically show why it works, things like that. There are some formulas here. I'm kind of just showing my work. It's not anything that you need to stress about memorizing, but I need you to understand what we're doing here with ANOVA. And again, one of the key concepts is we're actually testing the variances, and that leads us to an inference on the means. And real quick before we get into reading this, and I'll kind of explain it a little further, you should be thinking, if you just stop and think to yourself, how did we test a one sample mean? Well, we tested a one sample mean by finding a test statistic, and that test statistic was derived by the formula x bar minus mu over s divided by square root of n. We took the difference between x bar and mu. If we had one sample, we just said, what is that sample mean x bar? And then we subtracted mu naught. What do we think the mean could be? What do we hypothesize the mean to be, right? And we said x bar is a certain value, and it's so many units away from what we thought it would be. And so that helps us make an inference on where we think it's located, because that's what differences can tell you, location. And so it was relatively straightforward. We just said, here's one sample of what I think x bar is. How far away is it from what you think it should be? Very straightforward. When we went to 2 sample, we couldn't really do that as much, but what we focused in on was comparing one x bar to the other. We said if the 2 means should be the same thing or be very close to each other, we said, well, how far are they from each other? And that was a pretty straightforward idea as well. We said if one x bar is 8 and one x bar is 7, you say, oh, they're 1 unit apart. Okay, now we had to divide by a standard error, standard deviation, because we had to say, what does that 1 unit mean? What's the relative context, right, of these things that are supposed to be really far apart or not? And that's why we divided by some standard deviation in that denominator of that test statistic. But the numerator, again, was pretty straightforward. It was just how far apart are the 2 x bars. But now just extend that one more time to 3 means. How can you determine how far apart the 3 means are from each other? And this is where I want you to pause, and if I want to make sure what I said before makes sense. If you need to go back and listen to that 1 sample, 2 sample explanation again, that's really important for where I'm about to go with this next one, which is really crucial to understanding why we have to do things in a weird way with ANOVA. Okay, so make sure you understand what I just said about 1 sample mean and 2 sample mean testing, and those numerators being just differences, x bar from mu naught, x bar from another x bar. And then now when you get to 3 x bars, if I have 3 sample means, because this is testing 3 means or more, that means I have to take 3 samples and get 3 means. How would I tell you how far apart they are? Because you can't just subtract 2 of them, because what about the third one? You can't subtract all 3 because, think about it. What if the means are 8, 7, and 6? So you do 7 from 8 and you get 1, and then what do you do with the 6? You subtract it, now you get -5. What does that even mean? Right? There's no real good way to take 3 values and say how close are they? Okay? And so that creates a problem because you can't just do like x bar 1 minus x bar 2 minus x bar 3. Like intuitively, that's where you would want to go after what we did with two sample testing, but we can't do that because I think you can see just plugging in some numbers that would make no sense. That 876 example, it doesn't even matter the order you plug them in. What you get would be nonsense. It wouldn't actually mean anything. As opposed to a two sample, right? If one's 8 and one's 7, you subtract their 1 unit apart. That number 1 has meaning. But when you do 8 minus 7 minus 6 or 8 minus 6 minus 7 or whatever, the number wouldn't have meaning. So how do you figure out how far apart they all are? And so that's where we get into this bullet here. We start off with a foundational element that says, if we think about the variation, the sum of the variation between the group means and the variation within the groups adds up to the total variation. So we separate total variability, which is the variability of all the data points. Let's say I have 3 groups. Let's say I have 10 observations in each group. That means I have 30 total observations. It's saying take the variability of all 30 observations, and I can actually break that into 2 pieces. One piece is what's the variability between the means of the group, and the other one is the variability within each group. And it's this idea, and it seems a little bit wonky, but it's this idea that if I were to draw it on a piece of paper, if I were to take 3 different color markers, take a red, a green, and a blue, or 3 other colors, it doesn't really matter, and I were to put them as dots on a number line as my actual sample values, the question you're asking yourself is, what is the spread of the blue dots to each other? What is the spread of the red dots to each other? And what is the spread of the green dots to each other? That's within group variability. And then we're asking ourselves, but if I were to take the mean of the blue dots and the mean of the red dots and the mean of the green dots, what's the spread between the means? And those 2 components add up to the total variability of all 30, hypothetically 30 data points. In that scenario of 3 groups and 10 observations in each group. And so what we're measuring to make a determination about if the means are similar is we're going to say, well, how spread apart are those means relative to how spread apart are all the data points in general? That's the key concept that I want to leave you with here. We can't just do a location analysis like in 1 sample and 2 sample testing, where we just said X bar 1 was here, X bar 2 was here, oh, they're 2 units apart. Okay, that tells me a location measure. Now I need to standardize, and I could see if I think that the groups are different, because like we said, we can't just straightforward subtract. So what we do is we say, how variable, how spread apart are the group means from each other, but also how spread apart are all the points from each other? Because if the group means are really far apart from each other, then you might say they're different. But it's not just how far apart they are from each other, it's relative to how far apart are all of the points. Because if all of the points are really spread out and the group means are spread out too, it doesn't really tell you much. It's like, well, all the points are spread out, so maybe the means are spread out too. I don't know. But if we have a scenario where the means are spread apart, but there's not a lot of variability within group because all the blue dots are really, really close and all the red dots are really, really close and all the green dots are really, really close, I have 3 distinct groups. But if my group means are actually kind of close together, but all the points are spread out, that tells me that the means aren't really different just because all the points are spread out. So it's kind of a, do you have clear differences among your colors? So again, just think about it as a number line, draw out your points, take 3 different color pens and just say, eyeballing it, just say, do I have clear separation between my blue points and my red points and my green points? And that's what we're trying to do. Now we're going to do it mathematically. We're not going to eyeball it. We're going to mathematically say, do we have the separation in the red points from the blue points from the green points? And so then the question becomes, how do we measure that variability? We've already kind of talked about this idea a couple of times now, that we're measuring the variability between the groups and comparing that to the variability within the groups. How do we do that? So this first bullet here, or this next bullet here, talks about how to measure the variability between the groups. We do a weighted sum of squared differences between each sample mean, x bar sub I, and the overall x bar, which would be the overall mean of the data. You don't need to do that calculation. That's just kind of an FYI. Each square difference is multiplied by an appropriate group sample size in sub I. So again, the sub I is meaning the ith group. What you do need to know is that the quantity for this is called the sum of squares for the groups. And again, the formula, I'm just kind of showing you the work, just so that you know I'm not making this up out of thin air. But the numerator of our F statistic is the mean square for the group, which is going to be the sum of squares for the groups, sometimes called the sum of squares for treatment. That's why you see SST. You can see either one. It's kind of 50-50 in the literature as to which one is more commonly used. But the sum of the squares between the groups, or for the treatment, so sum of squares group, sum of square treatment, divide by k minus 1. Remember, k is the number of groups. That is the mean square treatment, or mean square for groups. Again, either nomenclature is appropriate. That value right there is the numerator of our F statistic. The denominator is the variability within the groups. Again, we're dealing with some individual standard deviations of groups, so S sub 1 squared to be the variance of group 1, S sub 2 squared to be the variance of group 2. Again, you don't need to know the math part of that. The idea is that the denominator of the F statistic is called mean square error, MSE, and that is the sum of the squared errors over capital N minus K, and capital N being the total number of observations, and K being the number of groups. Note that mean squared error is just a weighted average of the sample variance of the K groups. So if all of the sample sizes are equal, the mean squared error is simply the average of all of the variances. It's just a weighted average of variances. That's all that is. Note that our denominators are different. They both involve the number of groups, though. Okay. And so our test statistic, as we've already kind of talked about, is the ratio of mean squared treatment divided by mean squared error. That's the variability between the groups divided by the variability within the groups. We've kind of been flirting around talking about that idea. Now we're kind of formalizing it here. This is the main difference between our ANOVA testing as compared to our previous tests. I mentioned before, a lot of hypothesis testing is lather, rinse, repeat, and it is. This is the new part that you have to know, because every different hypothesis test is going to have a different test statistic. If you recall, we've learned 4 different types of tests so far, really. Now, we've learned a 5th, but the 5th one just acts like one of the other ones. We've learned a 1 sample mean, a 2 sample mean, a 1 sample proportion, and a 2 sample proportion. And those were all 4 very different tests. Now, the 2 sample dependent mean just acted like a 1 sample mean. So that's what I'm saying. We didn't really have a 5th one there. Notice all 4 of those had very different test statistics. And that's one of the main differences was what was the test statistic, what are the assumptions, and what distribution do we get from that test statistic. And so that's kind of just what we've been covering here so far, is that ANOVA, it's going to look very similar. You're going to see a lot of the same things. We're going to have to find a null and alternative hypothesis. We're going to have to come up with a test statistic. We're going to see, does it fall in the rejection region or not? We can find a p-value, and it's the same conclusion as before. But how do we find the test statistic? And here we have arrived at it finally, and that it's the mean squared treatment divided by the mean squared error. Okay. We'll see some examples through the notes and in the homework on this. You kind of need to be prepared to see a lot of different things. You need to be prepared to just be given an F statistic and your life is good. You need to be prepared to be given the mean squared treatment and mean squared error and divide out and then get the F statistic. You need to be prepared to be given the sum of the squares, as we talked about in the previous 2 slides. What if I give you the sum of squares of the groups or the sum of squares error, and I give you the other information? You should then be able to divide to get to mean squared treatment and mean squared error, and then divide those to get to the F statistic. So you kind of need to be able to take whatever you're given and work through to get to this F statistic. And then the last thing you should be wondering is, what are the degrees of freedom? Because we said there were 2 of them for every F. Well, the degrees of freedom are the things that we divided the sum of squares by. Remember, we divided the sum of squares of the groups by k minus 1, so the numerator degrees of freedom are k minus 1. The denominator is mean squared error, so we got that by taking the sum of the squared errors and dividing by capital N minus K, so that is the degrees of freedom for the denominator. And remember, we said from the start that the total variability can be broken down into these 2 components that could be added together, and so the total degrees of freedom are actually this piece plus this piece. And notice, if you add N minus K plus K minus 1, you get N minus 1, because that minus K plus K would cancel out. And look, this looks pretty familiar to you, because anytime we've done a test on means, whether it's 1 sample or a 2 sample, we've always done some form of n minus 1. Okay, and so it's a similar idea here. So you need to be able to identify what the numerator degrees of freedom are, the denominator degrees of freedom, and the total degrees of freedom. The total degrees of freedom will not play a part in the actual work, because when you go to your F table, you need to know the numerator degrees of freedom and the denominator. You aren't going to be asked for the total. The total is just an extra fact that we need to be able to find and report. Okay, but when we go to the F table, these are the two key pieces that we need. If you go back to that picture on the previous page of all the F curves, this would have been R1 and this would have been R2. This doesn't actually appear anywhere. It's just an extra fact.